So today we're going to start a new chapter talking about momentum, okay, and the relationship between objects in terms of their momentum when they're moving, their momentum when they start colliding. So we're going to deal with momentum and collisions in this chapter. So when we're talking about momentum, it really deals with Newton's first law, right? The first law was a law of inertia. That first law tells us that things in motion tend to stay in motion. Things at rest tend to stay at rest. So momentum helps us understand kind of the math behind that. An object that is in motion wants to stay in motion until it collides with something else, right? Until a non-zero force acts on it and changes that direction, or it has a collision with something. There's two main types of collisions that we're going to talk about in this chapter. The first of which is called an elastic collision, an elastic collision. Elastic collisions are when things hit and rebound off of each other. Okay, so they're going to hit, they're not going to stick together, they're going to hit and they're rebound off each other. So if you think of like playing pool, those billiard balls, when you would hit something with a cue ball and they bounce off, that's considered an elastic collision. And in that collision, all kinetic energy is conserved. So that means there should be, in a perfect elastic collision, there's an exact transfer, 100% transfer of energy from one object to the next. Okay, so there's no loss of energy in this collision at all. On the other side of that is something called an inelastic collision. So an inelastic collision is when two objects collide and they stick together after a collision. Okay, so in this particular instance, kinetic energy is not conserved. We lose some energy while we're doing this inelastic collision. So this might be an example of two cars smash into each other, right? They're in a wreck, they smash into each other, and they both continue to move in one singular direction because they're all tied up or knotted up. That's considered an inelastic collision. So these two things begin as separate objects, then when they collide, they stick together and move on as one object. Something that you should note for both of these types of collisions is that momentum is conserved for both of these types of collisions. Okay, momentum is conserved, although energy is not necessarily conserved. Momentum is, so that means that the total momentum of the system before the collision is going to equal the total momentum after the collision. And we're going to get into some equations that help us view that, but this is just a little introduction to that before we get there. So there is something for you to note with both of these types of collisions. Momentum is conserved, but energy is not necessarily. So now that we've talked about momentum and the overall picture of momentum, I want to get into the equation that goes with momentum. Okay, so momentum in itself means mass times velocity. Okay, or mass times velocity. Momentum is represented by a lowercase p. Lowercase p, and its equation is mass, which must be in kilograms, times velocity, which must be in meters per second. Okay, so this delta right here, all this means is change in, right? So this means final momentum minus initial momentum is equal to mass times final velocity minus initial velocity. That's what our delta means. Okay, momentum is a vector quantity. So tell me what two things we need in order for something to be a vector rather than a scalar. Vectors must have two things. Hopefully you can name those two things. Okay, a vector quantity means we must have both magnitude and direction. Okay, so vector quantity means we need both magnitude and direction. Okay, which of these components of momentum is considered a vector? Okay, mass is not a vector, velocity is a vector quantity, which is why momentum must also be a vector quantity. Okay, so when we're talking about momentum and it's the fact that it has to have both a magnitude and a direction, the direction of the momentum has to be in the same direction as the velocity. right? Since velocity is a vector, it's got a magnitude and a direction. Our momentum has to be in the same direction as that velocity vector. So if my velocity is in the westward direction, that means that my momentum is also heading west, right? I can't be moving west but have a momentum going in the eastward direction. That wouldn't make any sense. Okay, our units for momentum are kilograms times meters per second. There's no fancy short unit for this. This is our unit for momentum, kilogram times meters per second. Because kilograms means our mass must always be in kilograms, and our velocity must always be in meters per second. So if you have to do some conversions to get those two in the right units, you need to do that. So let's talk about this example here. A large truck and a small car are moving at the same speed. Okay, so envision these two objects moving down the highway at the same speed. Which is more difficult to slow down, the car, the small car, or the large truck? Okay, so you should have answered here that the large truck would be more difficult to slow down. Although these two objects are moving at the same speed, the large truck has a greater mass, which means that would result in a greater momentum. Okay, so let's say that the truck had a mass of 1,000 kilograms and the car had a mass of 500 kilograms. Oops, not 5,000, 500 kilograms. Okay, the momentum of the truck would be twice as much as the momentum of the car. So it's going to take twice as much force to slow that object down. All right. Let's try an example here. So go ahead and pause the video and get this written down, and we're going to start working through it. Okay, this tells us a runner's traveling 3.21 meters per second west. If the runner has a mass of 65 kilograms, what's the momentum of the runner? So our momentum is using the equation P equals mass times velocity. Right? We don't have to include the delta if we're not looking at a change in here. Okay, we can drop the delta because we don't have a final and initial velocity. We don't have a final and initial momentum. We're just looking at momentum itself. Okay, so P, which is momentum, we're going to take mass, which is 65 kilograms. Don't need to do any conversions there. And our velocity here is heading west, which means we need to include a negative 3.21. Okay, your final answer, you could just include the negative there or include the west there if you want, but this is going to give us a really clear indication that our velocity is negative or in the westward direction, and that our momentum should also be in the westward direction. Okay, so we can label that west, or we could also label it P equals negative 208.7 meters per second. Oh, not meters per second, that's the wrong units. Sorry. Our units for momentum are kilograms times meters per second. So I'll get that right. Okay. Either of those answers would be acceptable because this tells us that we're heading in the west direction. All right, another momentum problem here. It says a rolling boulder is found to have a momentum of 4,015 kilograms times meters per second east. If the velocity of the boulder is 16.4 meters per second, what is the mass? Okay, this time we were given our momentum, 4,015 kilogram meters per second, equals mass, which is what we're trying to solve for, times velocity. What do we know about the direction of the velocity here? Okay, not only is it positive, but since our momentum direction was east, that means that our velocity direction must also be east, okay, or be positive. We remember that because momentum has to be in the same direction as the velocity. Okay, so all we're going to do to solve for mass here is we're going to take 4,015 divided by 16.4, and we get a mass of 244.8 kilograms. So now that we've looked at the basic equation for momentum, we're going to look at the connection between momentum and force. Okay, so the connection between these two is that anytime we need to change momentum, there has to be a force that's acting on this object to change its momentum, right? An object's going to keep moving unless an outside force acts upon it. That's what our first Newton's law tells us. Our law of inertia tells us that. So in order for an object to change momentum, we've got to have some force that's acting on it, some non-zero net force acting on it to change the momentum of an object, okay, whether we're changing the momentum in speed or direction. Okay, remember that changes our vector either way, speed or direction. So Newton's second law normally tells us that the net force of something is equal to mass times acceleration, right? This symbol right here is sigma. That tells us the sum of. So really it's saying F net is equal to mass times acceleration. Okay, if we do some manipulating here, we can make F net equal to mass times change in velocity over change in time, because we know acceleration equals delta V over delta T. So all we did is we did a substitution here. Change in velocity over change in time is equal to acceleration. Okay, and I'm going to show you the derivation that it gets here to connect force and momentum. You don't necessarily have to have this derivation in your notes, but I'm going to show you how we get from Newton's second law to this new equation for force and momentum. Okay, what we did here was we combined mass times delta V all over delta T. So we took a fraction here, net force is equal to mass times delta V over delta T. We just combine these two, okay, since they're both in the numerator. And that's going to leave us with change in mass times velocity over change in time. Okay, so this term right here looks like the term for momentum that we just solved for. Okay, and that gives us a final new equation that we're going to need in our notes that says the force is equal to the change in momentum over change in time. Okay, so some force that's required to change this momentum, to take it from an initial to a final, is equal to the change in momentum over change in time. Okay, and remember, delta equals final minus initial. Final minus initial for delta. Okay, so always final minus initial. So let's go ahead and try this problem here. So go ahead and hit pause so you can get this written down, and we're going to try it together. What force is required to stop a 488 kilogram wagon moving at a velocity of 52 meters per second north in 2.3 seconds? So let's go ahead and take a look at what variables we have. Here's our overall equation that we need to use, right? Force is equal to change in momentum over change in time. But we're not given a momentum. We're given a mass and a velocity and a time. So our mass is 488. Our velocity initial, right? Our initial velocity is 52 meters per second. And our final velocity is 0, right? We don't have, it's coming to a stop. Okay, so that means our final velocity must be equal to 0, and our time is 2.3 seconds. Okay, so to find our change in momentum, delta P equals mass times delta V. We're going to go ahead and solve for our change in momentum here. Delta P is equal to mass times final minus initial velocity. Final velocity is 0 because it's coming to a stop. Our initial velocity was 52 meters per second north. So we're going to take 488 times negative 52, and that gives us a change in momentum of minus or negative 25,376 kilogram meters per second. Now to find the force that's required to make that change, we're going to take that change in momentum over our time. And that means the force required to stop this motion was 11,033 newtons. Okay, and the negative here, the negative that comes with this tells us that our force is coming, it's going south, right? It's going to the south. So originally our object was moving north, okay? And in order to stop that, we have to apply a force from the north to the south, right? Heading in the southerly direction to try to stop that object. Okay, so we're going to make that a negative 11,033 newtons or 11,033 newtons south. Okay, either way, but it's opposing that motion, so our force, it makes sense that our force comes out negative. All right, let's look at our next problem here. So go ahead and pause the video to get it written down. All right, so we're going to start here by looking at what this 55 Newton object, what's that term tell us? 55 newtons, that should ring a bell that is equal to F sub g. Okay, so that is not our mass, that is our weight. Okay, so in order to find the mass of the object, we're automatically going to take that 55 newtons, divide it by 9.8 to get the mass of our object. Okay, it tells us that it's traveling 36 meters per second, so our velocity is 36. If the force required to bring an object to a stop, so that means our final velocity is 0, and the force required to do that is 42 newtons. It asks us, how long did it take to come to a stop? So we want to find our time. Okay, again, we weren't given a momentum here. We weren't given our change in momentum. So if you can go ahead and solve this problem yourself, you can hit pause and do that. But I'm going to go ahead and work through what we're looking for here. We weren't given a momentum, so we're going to take delta P equals mass times delta V. Our change in momentum is equal to 5.61 times our final velocity minus our initial velocity. Okay, so 5.61 times negative 36 gives us negative 202 kilogram times meters per second. This time we were given our force, but we're going to use the equation force equals delta P over delta T. Our force was 42 newtons. Our momentum change was negative 202, and we're going to solve for time. Okay, so our trick when we have variables that are set up like this, our variables on the bottom, we're going to switch these two places. So that means T is equal to negative 202 divided by 42. Okay, and I guess we should make a little distinction here. Since our velocity initially was positive, that means the force required to bring it to a stop should be negative, so I didn't include that originally. But we can't ever have a negative time, so that should send up a red flag that something is a little bit wrong. But since our object was initially traveling at a positive velocity, right, it was traveling north, that means the force required to bring it to a stop is negative 42 newtons, and that wasn't included in the original wording of the problem, but it should have been. Okay, so that gives us a time equal to 4.81 seconds.